Hey physics students, Campbell here. In our third video on magnetism, we're going to talk about magnetic forces on current carrying wires. So if a magnetic field can exert a force on a moving charge, right, and current is just moving charges in a wire, then obviously magnetic fields will exert forces on current carrying wires. Now, direction, again, right-hand rule. Flat hand rule, right, that's our force rule. So if we imagine that we have a magnet and we run current through the wire, and we have current running in this example here, running like this in the wire. So at the top of the magnet, here's our magnetic field right north to south. So put your fingers to the right. Put your thumb into the page. Right, this is 3D, so imagine 3D. So into the page. What is the direction of your palm? So in current carrying wires, your thumb is the direction of the current, your fingers are the direction of the magnetic field, and your palm points in the direction of the force. So I know that charge is electrons, but remember we follow positive charge. So thumb in the direction of the current, which is going to be into the page. Fingers should be pointing to the right for you. Palm is pointing down. So the force on this wire is down, and it will deflect down, and I will demonstrate that in class. If we reverse the direction of the current, so now the current is coming out of the page, you're going to flip your hand over so that your fingers are still pointing to the right, right? That's still the magnetic field, but your thumb's now pointing out at you, and the force is up. So in fact, the wire will deflect up. It's actually pretty cool to watch. All right, now how about we calculate the magnitude of the force? I mean, we have our equation that force is QVB, but now we're dealing with current, so we don't really think about the amount of charge that's flowing. Right? We measure the current. But if you remember back to circuits, current is the amount of charge that flows per unit time. So somehow in our little QVB equation, we need to get something in here in terms of time. Well, think about velocity, right? What is velocity? Does velocity have a time component to it? Sure, right? Velocity is distance over time. So how about we think about distance in terms of length? Length of the wire over time. If I substitute that in for velocity, right, then I have my velocity component now as length over time, right, distance over time. And if I kind of move that t over, right, order of operation, doesn't really matter, right, q over t, well, there's current. So my equation for the force on a wire, if it's perpendicular to the magnetic field, is that force is the current times the magnetic field times the length, or what I like to actually call it flib. Flib. That's the force on a current carrying wire. Now, if it's not perpendicular to the magnetic field, well, then we got to throw in an angle, just like we do if the particle, and moving particles, if they're at an angle. So if we have our current, our wire, at some angle to the magnetic field that's not perpendicular, we need to take the sine of that angle, just like we do with charged particles. All right, pause the video and see if you can calculate this to determine the current that causes an upward force of 1.5 times 10 to the negative fourth. Well, if you did this right and plugged your numbers in right, you should find that the current is 2.44 amps. That's not too bad. All right, I got another question for you. Pause the video and see if you can find out the magnetic force on this wire in Earth's magnetic field. Earth's magnetic field has a magnitude of 5.5 times 10 to the negative fifth Tesla. Well, if you plug your equation into our flib equation with the sine of theta, because we've got an angle, you should have gotten 2.3 times 10 to the negative fourth newtons for a force. Not a big force, but Earth's magnetic field does exert forces on current carrying wires. Now, what if we take a loop? Take a loop and we put it in a magnetic field. And this is a square loop, but it could be a circular loop, doesn't really matter. But for the purposes of this slide, we're going to talk about a rectangular loop. It has a uniform magnetic, it's in a uniform magnetic field which is pointing directly to the right, and I have current flowing counterclockwise through the loop. What I want to know is, what is the direction of the force on section AB of the wire? All right, well, put your fingers, flat hand, put your fingers to the right, and put your thumb parallel to that. Oh, wait, it's parallel. So that means our force is 0, right? Sine of 0 is 0. Oh, cool. What about the direction of the force on section BC? Well, again, fingers to the right, thumb points up. What is the direction that your palm is pointing? Well, hopefully you said that your palm is pointing into the page or into the screen of your computer. Lastly, what is the direction of the force on section DA of the wire? Well, fingers should still be pointing to the right, but now you're going to rotate your hand so your thumb is down. If you rotate your hand so your thumb is down, your palm should be pointing at you or out of the page. Now, I could have asked you also about the force on section CD of wire, but obviously, again, the current is running parallel. Sine of 0 is 0. So there's no force on that section of wire. But this is an interesting thing then. So the forces would be equal, right, on each section of wire, on section BC and AD, but one's down and one's up, or into the page, out of the page. So you know what that means is, if it's possible, the current, when there's current running through a loop, even though the net forces on each side of the loop are going to be equal, regardless of whether it's a rectangle or a square or a circle or whatever, there's going to be a net torque. So if that loop is not parallel to the field, if the normal to the loop, the normal would be a line that's drawn perpendicular to the surface of the loop, right? Just like a normal is perpendicular to a surface, a normal force. If the normal to the loop is not parallel to the field, then there's going to be a net torque on this loop, and the loop will rotate. In fact, loops rotate in magnetic fields, and that's actually a great application of motors and generators. And in fact, in another week or two, we're going to be building some motors. Pretty cool. So how do you keep them rotating though, right? Because once we get this loop rotated so that its normal is parallel to the field, the force now on these top and bottom sections is going to be straight up and down. So how do we keep it rotating? Think about that. We'll talk about it in class. Now, if I have two wires present, right, both wires are creating magnetic fields at the location of the other wire, which means that they're exerting forces on other wires. So when I have multiple wires in space, they're creating multiple magnetic fields, and all of those fields are generating forces at the location of the other wires. Now, if we think about, let's look at this wire whose current is running to the right. We use the claw rule to find out the direction of the magnetic field. So if you think about it, at point P above the wire, make your claw. Your thumb should point to the right, and your knuckles should be above. Your fingers should be pointing out at you. So the direction of the magnetic field due to wire 1 at point P is out of the page. But let's throw another wire in. What if we put wire 2 in here? And we have wire 2 running current in the same direction. Well, so now I've got this magnetic field from wire 1, so if I put wire 2 in there, and it's got moving charges in it, right, it's got current, it's going to feel a force due to the magnetic field from wire 1. And now if we think about it from the right-hand rule, what is the direction of that force? Well, we just said the magnetic field was out of the page, so rotate your hand so that the magnetic field is out of the page pointing at you. Put your thumb to the right. What is the direction of your palm? Well, your palm should be pointing down, so the force should be down. Did you get that? But if we start with wire 2, right, and forget about wire 1 for a moment, what is the direction of the magnetic field from wire 2 at the point below it, where wire 1 was? Well, claw rule, right, that finds the direction of the magnetic field from a current carrying wire. Right, finger to the right, your knuckles are going to be below the wire, below your thumb. What's the direction that your fingers are pointing? All right, your fingers are going to be pointing into the page, which means that below wire 1, there is a magnetic field that is pointing into the page. So when we put wire 2 back in there, wire 1 back in there, with its current running to the right, it's going to feel a force. from wire 2. Oh my gosh, they're exerting equal but opposite forces on each other. But what is the direction of that force? Well, put your fingers into the page, right? That's the way we said the magnetic field was pointing, down below wire 2. Put your thumb to the right. What way is your palm pointing? Your palm is pointing up. Cool! So the force on wire 2 from wire 1 is down. The force on wire 1 from wire 2 is up. That means it's an attractive force. And in fact, if you're not good at the right-hand rule, you might want to remember this. If you have parallel wires with current running in the same direction, they exert attractive forces on each other because the forces, one's up and one's down. But what happens if we flip the direction? Well, if we flip the direction, think about it. Actually, see if you can figure it out. Figure out the direction of the magnetic fields and the direction of the forces. If you do it right, you're going to find out that if wires are creating current that are traveling in opposite directions, they actually exert repulsive forces on each other. So if you're not good at the right-hand rules, you may want to memorize that. But what about the magnitude of the force? How is the magnitude of the force? Well, if we think about it, down below here at wire 1, all right, the magnitude of the magnetic field generated from wire 2, right, would be Biot-Savart's law. So the permeability constant times the current from wire 2 divided by 2 pi and the distance between the wires. And the force equation, right, is FLIB. So the force on wire 1 is the current through wire 1 times the magnetic field generated by wire 2 times the length of the wire. So I can take this equation, right, and substitute it in here. And then, of course, we got to do some cancellations. Or simplifications, I should say. And we get this equation, that the force per unit length of wire is the constant, mu sub naught, times the currents in both wires, divided by 2 pi, the distance between them. Or remember that the coefficient is 4, or the constant is 4 pi times 10 to the negative 7th. So it's really 2 times 10 to the negative 7th times each current divided by the distance between the wires. Now that is the force per unit length. So if you're looking at a specific length, then you would move that L, where's my cursor there, that L over here. Pretty cool. All right, let's see if you can calculate out the mutual force per unit length of these wires. They are 5 centimeters apart. Make sure you work in meters. Pause the video. See if you get the right answer. If you did this right, you should get an answer of 9.6 times 10 to the negative 5th, and it's a force per unit length, so newtons over meters. And because the wires are running current in opposite directions, that is repulsive. It's the only time that opposites are repulsive, right? Usually opposites attract. All right, how'd you do? Fill out your Google form, and I'll see you in class.